Okay, class, so we move into section 12.7. 12.7 deals with triple integrals. Now, where would you use a triple integral? Well, one application would be if you wanted to find a center of mass for a solid that has variable density. In that situation, you would need to use triple integrals to do that. Okay, and we'll see some other applications as well in chapter 13. In chapter 13, we actually bring everything together, that all the concepts you've learned in chapters 9 through 12, and we're going to see a lot of applications. But triple integrals now is what we're talking about. So, okay, let's take a look here at figure 1. Hold on here. Let me just see here. So if you put this down a little bit. If you have a solid and you pick, well, I want to say this the right way. There's a box, okay? You see here in this figure, this is actually figure 1, what we're looking at. You see a box. And we take the box and break it up into a bunch of little boxes, okay? A bunch of little sub boxes. And every sub box has its little volume. And the little volume is given by delta y times delta x times delta z. So we can talk about a triple integral over the box by saying, all right, we're going to take a function and evaluate it at different points. And at each point, we're going to multiply the function value at the point by the volume of the box. So in other words, this is what I'm talking about, a triple Riemann sum. So you see, the function now is not of 2 variables. It's a function of 3 variables, x, y, and z. So as we vary x, y, and z, we move around a solid, different points in a solid, and compute the function at those points, and then we multiply by the piece of volume at where that point is. That is a triple Riemann sum. And obviously, if you take an infinite number of points in the solid, in that case it was a box, but if you take an infinite number of points and let L, M, and N go to infinity, then this triple Riemann sum is going to become a triple integral. That's what you're going to have, a triple integral. So just like when you did double integrals, you did an iteration, right? You iterated the double integral so that you would integrate with respect to one variable and then get your result and then integrate with respect to the other variable. Well, with triple integrals, you're not going to iterate twice, but you're going to iterate 3 times. Now, with double integrals, you had 2 types of regions. You had a type 1 and a type 2, and those regions were in the xy plane. But with triple integrals, since you're integrating over a solid, okay, you're going to have 3 different types of regions. Okay. Now let me take you. Let me show you. Okay. So this is figure 2. This is a type 1 solid region. So your solid E is bounded above and below by functions of x and y, and then the solid. I want to say this the right way. If you were to project the solid down into the xy plane, you would have a region D. So what would a type 1 solid region look like as a triple integral? Let me see, maybe I can have it together here. Yeah, that's what it would be. So you see, a double integral, well, the triple integral, the first integral goes from a top surface to a bottom surface, if it's a type 1 region. Top surface to a bottom surface. Those are the solid is bounded above and below by a surface. The bottom surface is given by the function u1 of xy. The top surface is given by the function u2 of xy. And after you integrate that with respect to z, okay, because z is equal, you can see in region 1 in the picture above, the top and bottom surfaces are you know, there are surfaces such that z is a function of x and y. So after you integrate with respect to z, then you have a double integral with respect to x and y. And that's going to then now basically be like section 12.3 and 12.4. That's a type 1 solid region. Okay, now you can have, I want to be a little bit careful here. Let me just see here. One moment. Let me put in a little more detail here. Yeah, so if we wrote out explicitly what the limits are with respect to z, y, and x, those would be your limits. Okay, because if you go to region 1, if we go back to region 1, okay, you see I'm sorry, solid, type 1 solid. The type 1 solid region, I don't, when I think of region, I think two dimensions. The type 1 solid is bounded above and below by a surface, okay, above and below by a surface. But then if there's another picture I'm looking for. Yeah. So here, hold on here. You have a type 1 solid. It's bounded above and below by a surface. But then when you project the surface down into the xy plane, it's bounded above and below on that region D by g1 of x and g2 of x. Okay, and so if you write it out explicitly, this would be your those would be your limits. However, see that? However, you could have a situation where in figure 4, you have a type 1 solid region, but when you project the solid down into the xy plane, you have a type 2 region. Remember, region D's from section 12.3, the region D in the xy plane can be a type 1 or a type 2. Type 1 is when the region D is bounded above by a function above and a function below. Type 2 is when the region D in the xy plane is bounded on the left by a function on the left and a function on the right. And in this case, your for you know, figure 4 there, those would be the limits. So you see, you don't do dy dx, you do dx dy after dz. You do dx dy. So your knowledge in from sections 12.3 will come into play. Now I'll show you two more solids here real quick, because we're almost out of time. Okay, so here's figure 7. Here's figure 7. Here you have a solid E that's bounded by two functions. X is a function of y and z. Okay, and so you're going to integrate with respect, since the surfaces are functions with respect to y and z. You're going to integrate with respect to x first. And then the region D gets projected into the yz plane. So then you're going to have either dy dz or dz dy. And so this would be, well, this would be how you would do the integration. And then, you know, they're not being specific in terms of dA, whether it's dx dz or dz dx. One more real quick here. I know we're at the end. Type 3 region, you can have a solid where the bounding surfaces are functions of x and z. Okay, so that's what a type 3 region would look like. And this means you would integrate with respect to y first, and then you would integrate with respect to either x and z or z and x. It depends what your region D looks like. And so that would give you something, hold on here. Let's see. One moment, class. Where is it at? Forgive me, I got to find it. So what I'm trying to say, I might have said this, I don't know if I said this right, but look at figure 7, the type 2 region. Look at your bounding surfaces. The surfaces bound the solid E to the right and along the x-axis, functions of y and z, and so your integration would be as you see in the triple integral above. Okay. And then the other choice is, I think I had this mixed. It's because the pictures didn't, I assumed the pictures would come, you know, I just had the order of the pictures wrong. Type 3 region, here the solid E is bounded by surfaces to the right and the left along the y-axis. So you're going to integrate with respect to y first, and then integrate with respect to x and z. So that would look like, yeah, that don't do that. Don't do that. That would look like that. Okay, so give me a thumbs up if this is making some sense to you, at least initially. We'll review it again in the next class. But all right, you start to hopefully see the pattern here. Thank you, Yeva. Thank you, Matthew. Thank you, Norina. Well, thank you, Christia. Thank you, Samuel. Well, on that note, I will make the assignments active. Don't worry, I'm going to do that in a few minutes. Thank you for a great class, everybody. Good luck if you're, you know, doing the first or second version of your exam. Thank you, and work hard, please. We're not too far away from the end. Thank you, Simon. Thank you, Yeva. Thank you, Mary. Appreciate it. Thank you, Matthew. Appreciate it. Thank you, Christopher. Appreciate it. Thank you, Norina. Thank you, Lexi. Okay. I will stop the recording.